Hello everyone. Today we're going to talk about normal random variables and normal distributions. We say that x, which is a random variable, has a normal distribution, or we simply say that x is normally distributed with parameters mu and sigma squared if the density of x is given by the following function. So the density function is 1 over the square root of a 2 pi times sigma, it's on the bottom, and then e to the negative of x minus mu squared over 2 sigma squared when x is greater than negative infinity, less than infinity. Okay. It's a little bit complicated to see that. What I want to emphasize is that the core is e to the negative x squared. Sometimes we put 2 here, okay? But the thing is the e to the negative x squared. And then you have a sort of parameter mu and sigma, they represent something we're going to talk about. And then you need to have the normal number so that the integral of everything would be 1 because we're talking about PDF. So this is basically the norming constant. Okay, so the core is e to the negative x squared. In calculus, we know that e to the negative x squared is a bell-shaped curve. Okay, so this density also has a bell-shaped curve. Now, the when we change when we change mu and sigma, so how would these parameters change the shape of the graph? Mu is the shifting parameter. So originally we have a normal curve. So I'm gonna just draw a normal curve, any kind of normal curve. Shape, anything fancy shape? No, no, no. Okay. So I'm gonna just draw a normal curve. It should be symmetric with respect to the the top. All right. So when you add a mu, positive mu, if mu is greater than 0 and you add a mu, then it will shift to the right. If mu is negative, you add a mu to this and it shift to the left. Later on, we know that mu is really just the mean. So for this one, this is our mu. It's the mean because it's symmetric. So the middle point represents the mean. And how can sigma changes the shape? Well, when sigma gets bigger, then it's flatter. It has a more uh, viability. So it was something like this. It doesn't. Okay, that's fine. So something like that. And when sigma is smaller, then it will be something like this. Okay. Sigma is smaller. I didn't draw very well, but I hope you get the good sense. So it's this sigma 1, sigma 2, and sigma 3. We know sigma 1 is smaller than sigma 2, less than sigma 3. So you have a larger standard deviation, well, sigma actually is standard deviation. So you have a larger sigma, it's flatter and it has a heavier tails. When sigma is smaller, then it's more steeper and then it has a lighter tails. So when we say tails, like these kind of things are tails, this side, tails, tails, tails. Okay. Um, so how can we find the mean and standard deviation of of this density of this distribution, it will be a little bit more work, some work. So if you're not interested, you can skip this part. By the definition, say we have x, which is a random variable, which follows this density. Oh, by the way, the density is also denoted by n, which means normal. Not zero, it's mu. Use our standard mean, it's a parameter, and then you have a sigma square. Sigma square is the variance, but we're going to show that, okay? We have this density. We want to show that sigma is, mu is indeed the mean and sigma is indeed the standard deviation. All right, so let's try to work it out. It's a little bit tedious, and if you are not interested, you can skip. So e of x, that is the integral from negative infinity to infinity, x times the density dx. So we have 1 over the square root of 2 pi sigma times, well, let's put x here, and e to the negative x minus mu squared over 2 sigma squared dx. The key is to use a substitution. So we let, let's do y, be x minus mu. So x equals y plus mu, dx equals dy, okay? And when x runs from negative infinity to infinity, we know y also runs from negative infinity to infinity. So we have everything but negative integral from negative infinity to infinity. X equals y plus mu. And then I have still have a square root of 2 pi times sigma e to the negative. Now you have a y squared over 2 sigma squared, and dx equals dy, so I have that. And I have y plus mu. I'm going to break it up, negative infinity to infinity. And I have y over the square root of 2 pi times sigma. This is just constant. And I have that, then plus negative infinity to infinity. I have a mu on the top, bottom still 2 square root 2 pi times sigma, e to the negative y squared over 2 sigma squared dy. Okay. Now it's a tricky part. It's not actually not hard, but it's tricky. So when we look at this integral, by the way, it's the integral from negative infinity to infinity. But we're going to treat sort of treating negative infinity or positive infinity to some number. Okay, you can consider it a limit, but sometimes we can just treat it as a number in some sense, okay, artificial numbers. All right, so we actually can show this integral exists. Okay, it's a sort of convergent. And there's a very interesting property of this function. This function, I claim this integral is 0. Why is that? Because it's a odd function. Okay, you plug in negative y, you would get a negative function. And function is odd if we have this kind of property. Okay, because your y squared here is even, but this is odd. So you plug in negative y, you do get negative of fy. This f is general again, not that one. Maybe I should use g here. Maybe I just use g as the general function when we talk about odd function g of negative y equals negative of g of y. Okay, so it's odd function. So this is odd function, and this it's actually interval from negative infinity to infinity. It's not finite, but again, I said we can treat negative infinity, positive infinity as artificial numbers. We can, as long as the integral it exists, convergent. So anyway, it's the interval here is symmetric with respect to the origin. So the uh, the integral is zero. Okay, so something like this. You have let's just draw something which is not exactly, maybe it's this function, but I think this is very similar to this function. It looks like that. Okay, and it's an odd function, and the area, is this area equal this area, but in terms of integral, this is negative, so you cancel out to get zero. So anyway, it's zero. And the second part, I'm going to move out mu, and then inside you have 1 over the square root of 2 pi sigma e to the negative y squared over 2 sigma squared dy. Okay. Also, there's a trick we can use. Notice this thing. This is actually a density function. It's a density function for normal distribution with mean zero, with mu zero. Okay, you just look at this density and you let mu equal zero, you would get this thing. It's a density function. You integrate from negative infinity to infinity, you get one. So this is mu. So we proved that the mean is mu. To prove that the standard deviation is sigma, that needs more work because now you have x squared here. We need to find e of x squared. Then you still do the substitution, but then you need to uh, you let's see. I think you need some integration by parts as well. So I'm debating whether I should do it. Let me just write it down very quickly. By the way, if we, yeah, let's just write down something, and then we see if it's very complicated, then I'm gonna not do it. So e of x squared equals the integral from negative infinity to infinity x squared times 1 over the square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared dx. Okay. Let's do a to do substitution. So again, you have a y equals x minus mu, x equals y plus mu. So, and also the lower limit, upper limit doesn't change. We just did that. So I have y plus mu then squared times 1 over the square root of 2 pi sigma e to the negative y squared over 2 sigma squared dy. Okay, dx, dy are the same. Okay, so we're going to expand y plus mu squared. So I have a negative infinity to infinity y squared plus 2 mu y plus mu squared. And then you have 1 over the square root of 2 pi sigma e to the negative y squared over 2 sigma squared y. Okay. And I claim that this thing will disappear because 2 mu y times this function, it's odd function like what we did earlier. So the integral would be 0. And then mu squared times this integral, the integral will be just mu squared because it's a density function. You integrate from negative infinity to infinity, you get to 1. So essentially we have a negative infinity to infinity y squared times 1 over the square root of 2 pi sigma e to the negative y squared over 2 sigma squared. And then you have a mu squared. Okay, so dy here. All right. So let's do some substitution as well, I think. So y over sigma, let's treat it as t, and uh, so y equals sigma t, so dy, um, but we have y squared, so if let's do, maybe I do that, dy d2, uh, that one. Let's not do that for the moment. Okay, so I have y over sigma equals t and y equals sigma t squared. So I have a mu squared plus the integral from negative infinity to infinity. Y squared equals what? Y squared equals sigma squared times t squared times 1 over the square root of 2 pi sigma times e to the negative y square over sigma squared, that's t squared, so t squared over 2, and then dy equals sigma times dt. Okay. All right. So I have this one, so negative infinity to infinity. You have a sigma square, sigma cancels out. So this one cancels out. I still have sigma squared outside. I move it out. I have t squared 1 over the square root of 2 pi e to the negative t squared over 2 dt. So what is that? Hmm. This is a density function. But I have t squared. Let's continue. I'm gonna erase this part. Do I have enough space? I think I'm okay with that. So notice that the the derivative of this term uh, is no, that's actually not what I wanted to say. The antiderivative. The antiderivative of this quantity is actually not very nice. It doesn't have a explicit form. But when you think about you differentiate this, you would have a negative t in front of it. So you sort of differentiate it, you get e to the still that, and then you multiply by the derivative of the exponent, you have negative 2t divided by t divided by 2, you get negative t. So this is the derivative of this thing, but uh, this is antiderivative of this one. So I do have t here. So I'm going to break up the t into like t times t and use that t for the derivative exponent for e to the negative x squared thing, e to the negative t squared thing. So what I'm going to do is this. You have t times negative t. So I should put negative here as well. And 1 over the square root of 2 pi e to the negative t squared over 2 dt. And this thing is d of negative 1 over the square root of 2 pi. Hold on a second. I don't need the negative t there. So actually, I don't need the negative t here, just t times t. And I deal with this negative sign in the antiderivative, so I'm okay with that. E to the negative t squared over 2. So the thing is that you differentiate this, you would get t times, you get this term, okay? So I use integration by parts, u dv equals uv minus v du. Okay, this is the version I like. So that equals, move sigma squared is still there. So this is like our u, this is our v. So I have t times negative 1 over the square root of 2 pi times e to the negative t squared over 2, t from negative infinity to infinity, minus, we're going to switch, okay? We're going to switch these two. But you have not minus here. This is minus, and it cancels out. With this minus, it becomes positive. Negative infinity to infinity, 1 over the square root of 2 pi, e to the negative t squared over 2 dt. Okay. I need some space here, but actually we're very quick. It's going to be quick. All right, so on this term, we said in another video, when t goes to infinity, e to the negative t squared goes to 0 much, much faster than t going to infinity. So eventually this e to the negative t squared over 2 dominates when t goes to infinity. It doesn't matter negative infinity or positive infinity because t squared is going to positive infinity, but you have a negative sign in front of it. So e to the negative t squared over 2 goes to 0. And it's faster than t going to infinity, so this will disappear. It's just 0. And this term, you notice that this is just a density when mu equals 0 and sigma equals 0. So originally we have this density function here, f of x equals 1 over the square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared dx. No dx. It's a density function, it's not dx. Okay. X is greater than negative infinity, less than infinity. So when mu equals 0, sigma equals 1, you would get this thing. It's actually called the standard normal density function. But anyway, it's a density function. So you integrate it, you'll get 1. So eventually you get sigma squared. Okay. So originally here you have a sigma squared plus mu squared because when you expand it, y squared plus 2 mu y plus mu squared This term will disappear when you combine with this, it will disappear in terms of integral because it's odd function. And mu squared times this integral is mu squared. So eventually you have mu squared plus sigma squared. And then the variance equals the second moment minus the first moment squared. So you have a mu squared plus sigma squared minus mu squared, which is sigma squared. So the sigma squared is indeed the variance, and the standard deviation is sigma. So these notations match. Um, so I did go through these things. So I want you to have some sense about the density function of the normal distribution. If you take a prop stats course, I mean, especially probability course at this level, calculus-based level, it's really good to know the density of a normal distribution. Okay. All right, so that's about getting the mu and sigma. Remember, at the beginning, we just define this density function without knowing the meaning of sigma and mu, but now we showed, given this density, mu is indeed the mean and expectation, okay? And sigma is indeed the standard deviation. All right. We have a very important property. So if x is a normally distributed, then ax plus b is also normally distributed. A is a constant, b is a constant, x is a random variable. In fact, if x has a normal distribution with mean mu and standard deviation sigma, and then ax plus b is also normally distributed with mean a times mu plus b, because the new expectation is linear, right? So it is a times e of x plus b. So yeah, a mu plus b as the new mean. And the variance of ax plus b, b doesn't affect the variance. You just add a constant to the random variable. It doesn't change the shape. So you have a variance of a of x, and then you have a squared times the variance of x. So I have a new variance a over or a sigma squared. Okay, so that's the new distribution, which is normal with mean a and mu plus b and the variance a squared b squared. Okay. Uh, by the way, many textbooks use this notation for normal distribution with mean, mu, and standard deviation sigma, but occasionally you will see some kind of this notation, okay, mu and sigma. So you need to know what the notation is in the textbook. For example, if you see you have, let's say, 1 and 4. And what is that for? For means a standard deviation or standard deviation or variance. You really need to know the meaning of the notation in the textbook. In our notation, for our notation, this means the set standard deviation is 2. But if the textbook use this notation, then the standard deviation is actually 4. So this is something I want to mention. Uh, this notation is indeed very common, okay, but I know some uh, textbooks, especially in economics, they use mu sigma. Okay. So based on this fact, okay, this property, we have uh, and standard normal random variable. How can we get that? We define z, which is the standard normal random variable. Define this to be x minus mu over sigma. The minus mu, okay, it's kind of centering the original x. So you put the distribution to the y-axis. The y-axis will be the axiom of symmetry. And divided by sigma is normal, we call it normalizing. Okay, so the whole thing is called standardizing x. And this has a normal distribution, that's no problem. And the mean of z would be 0 because you have x over sigma minus, well, I mean, I don't need to do that at all. It's just x minus mu over sigma. You move out sigma, and you have expectation of x minus mu. It's expectation of x minus the expectation of mu, but the expectation of mu is mu itself, so it's just 0, 0. And the standard deviation, so the variance of x minus mu over sigma, that's 1 over sigma squared, and the variance of x minus mu, it will be still the variance of x for this term, because adding minus mu, adding or subtracting mu doesn't really change the variance, so it's just 1. All right, so z we call the standard normal random variable. It has a normal distribution with mean 0 and standard deviation 1. And we would call this standard normal distribution, standard normal distribution. This is probably the single most important distribution in the probability theory. Because of this fact, if we, well, actually, I wanted to say something before I move on to that. So suppose we have a random variable, say normal distribution with mean, let's say mean 0, okay? And the standard deviation, say 2. So if we wanted to find x, say less than or equal to 3, how can I do that? So essentially, you're gonna take the integral from -infinity to 3, and then we have 1 over the square root of 2 pi sigma, which is square root of 2. Oh my God, okay, so maybe I should just square here. So then you have 2 here, e to the negative x minus mu x squared over 2 times sigma, which is 4. Sigma is 2 dx. So if you know this fact from calculus, we know that this one actually doesn't have a explicit a elementary function as its antiderivative. Okay, elementary functions are the functions you study a lot in calculus. Polynomial, rational functions, exponential, log, sine, cosine, trig function, and so forth. It doesn't have a explicit antiderivative if you only use those functions. So, which means it's very difficult to calculate this integral. Okay, but because of this fact, because of the standard of this fact, I only need to make the people actually, not me, the people only need one table for standard normal distribution, which is called standard normal distribution table. And we can use that table to calculate all the probabilities, at least in approximation, in approximation sense. Okay. All right. So let's look at the standard normal distribution table. Some textbooks have two sides, negative side and positive side. But because the normal distribution, standard normal distribution is symmetric, so we really don't need two sides. But some textbooks would make it easier. So if you wanted to use two sides, that is okay. Um, So there are two types of problems I want you to know. And even though you have a calculator or even computer to calculate the probabilities, but as a training, as understanding the area and the probability, we usually use this as a kind of a training tool for you to get better sense about uh, like what I said, the area and the relation between the area and the probabilities. So it's still good to be able to use the table, but it would be less important than it was before. Like in earlier years, we had a table for log functions, but now we don't. Anyway, so for each table, when you see a table, you need to try to look at the table, look at the graph. It shows what it means. Okay. Some textbooks would have a table which only the shows this part. Okay. And if you look at the numbers here, these numbers will be less than half. So you need to be careful about what these numbers mean for a particular table. So for this table, it's a cumulative function basically. These numbers show cumulative probabilities. That's shown from this graph. So everything under the curve to the left of z. That's what it means. Z is here. This table, uh, Z is obtained from combining the first column and the first row. Okay, so let me show you an example first. So if we wanted to find Z is less than 2.1, what does that really mean? Okay, so Z is 2.1. So look, 2.1 is here. So I'm sorry, I'm going to change it to 2.14. Maybe that's more interesting. Okay, 2.14. What means is that you look at the first column, you get 2.1, and then you look at 0.04. So this number is our probability. Okay, so this would be 0.9838. All right. Sometimes when you have something like 2.145, then normally we just interpolate two values. So it will be the average of these two numbers. Uh, as far as approximation we concern, it's okay to just take an average, even though it's not very accurate because the curve is like this. It's not horizontal. All right. Okay. So what about the probability of z greater than 2.14? How can we do that? So I want you to, so normally I want people to draw a curve like that and then put 2.14 here and you see it's this side. Uh, this side, this area is not shown uh, here in the main part of the table. But you understand it's symmetric, so I know the probability of a z less than 2.14. That's known. And so you can get this area from 1 minus. So it's 1 minus. Uh, this probability is somewhere 2.14. We just marked it. Okay, so it's this thing equals 1.1 minus 0.9838. Okay, sometimes we would call this type of area so tail probability. Okay, so how about the probability of z is greater than negative 1.12 less than 3.24, just random numbers. Okay, so you draw a curve. This curve's ugly, but I think it's okay. So negative 1.12 and 3.24. So it's between, it's under the curve between these two numbers. So it will be the same as the probability of z less than 3.24 minus the probability of z less than negative 1.12. This one is pretty easy to find from the 3.24. So where is that probability? 3.24 again. This. So it's 0. 9994. So it's less than negative 1.12. So it's actually somewhere here. Okay. By symmetry, this probability equals the probability of z greater than 1.12. That's 1 minus the probability of z less than 1.12. Or here, less than or less than equal to, I really don't care because in terms of the probabilities, they are the same because normal distribution is continuous. Okay. So that will be so it's minus 1 minus 1.12. 1.12. So it's 0.86. All right. So that's how you get it. If you have two parts of the table like negative number, then it's pretty easy to get distance from the table. Okay. Some table does give a left side. So okay, so this is one type of problem you need to know, which is when you need to figure out, you need to be able to use table to find this type of probability. The second type is to find the probability for any normal random variable in a particular interval. Okay. So the idea is this, you're going to standardize X. So you standardize it by subtracting mu and dividing it by sigma. And then you need to do everything to the other two parts. You need to do the same thing. Once you standardize it, it becomes Z. So it is the probability of Z less than B minus mu over sigma and then greater than A minus mu over sigma. By the way, sometimes people use phi for the CDF of the standard normal distribution. So there will be B minus mu over sigma minus phi of A minus mu over sigma. I don't really want you to try to memorize these processes. I mean, notations and formulas. The process actually you need to know. The key process is standardizing. So let's have a look at an example. So X has a normal distribution, which mean, say 1, and we have a, say 4 squared, okay? And we try to figure out the probability of X greater than, let's do some number, 3 maybe, 3.12 maybe. Put a negative sign here, and less than 2.12, 12, 20, 16, maybe 16. Okay. So what we do is to standardize X. So that equals, well, yeah, let's standardize it. So you have X minus mu divided by standard deviation 4. So you have negative 3.12 minus 1 over 4 less than 2.16 minus 1 over 4. So that equals the probability of Z, not standard normal random variable. 1.16 divided by 4, what is that? So 0.29. Okay. And then you have a negative 4.12 divided by 4. So negative 1.03. Okay. That's phi of 0.29 minus phi of negative 1.03. This one is pretty easy, 0.29, which is here, 0.29. So 0.6141 minus, we don't have the left side, so we're gonna have to do 1 minus phi of 1.03. Okay, the negative 1.03 phi of that is this area that equals this area, which equals 1 minus this area. Okay, 1 minus this area. Okay, and then we look at the table. Plus what is phi 1.031.03, so 0.8485. All right. Um, 0.29. Okay. Yeah. Even though these two numbers are sort of large, but the standard deviation is 4. That's pretty big. Um, so uh, the probably I want to show you the when we standardize, what really does that mean? So originally we have a density. I have this graph. I'm not sure how I can draw the graph nicely. Okay, so you have y of 0, you have x, normal with mean 1. So you have something like this. Oh, by the way, the the curve has an inflection point at its standard deviation. So it's a bell-shaped curve, right? All right. All right. So this is our mean, and the standard deviation of the curve has a inflection point at this point. So what did I did? Sorry, I forgot these two numbers. X greater than negative 3.12, I guess, less than 2.16. Is that right? So what it means is this area, so negative 3.112 and 2.16 somewhere here. So this is the area that we are looking for. And then you have a standard normal uh, distribution. So you draw that. I'm gonna shift it because that is too squeezed to the right, to the left. And so you have so this is standard normal. One. Probably it's a little bit steeper because I have a standard deviation which is 1. Okay. And after you do the standardizations, you have x minus mean over 4. The curve, original curve becomes this standard normal curve, and this is 1. And the uh, so negative 4.12 over 4, it's negative 1.03, so somewhere here. And then you have a 2.16 minus 1 over 4, you get 1.16 over 4 equals 0.29, which is somewhere here. What this equation means means these two areas are the same. Okay, these two areas are the same. Of course, I didn't draw them by scale, but theoretically, these areas are the same. All right. Okay. So this is another type of problem you need to know. Given a general normal distribution, you find the probability that a random variable is between an interval. And then you need to know the backwards type of problem, which means the probability is given, and you need to know the sort of critical value. Well, in statistics, we call it the critical value. For example, find little z such that the probability of capital Z less than some little z equals 0. Say, let's do 9564. Okay. Now, this is a probability. You cannot look at, oh, 0.9 is here, and then you have 5, 6, or somewhere here. That's wrong, okay? These are the z-values, not the probabilities. Z-values are from x-axis. They're on x-axis. It could be really large, could be negatively large, could be close to 0, but the probabilities are always from 0 to 1. So this is actually probability, 0.9564. So you need to look at this number in the main part of the table. So I get this one. Well, I just look at it. That's why I put this number there. So little z is actually 1.71. Okay, that's our little z. Okay. Um, let's do another problem. So what about the probability of z greater than little z equals some, I don't know, 0.274, something like that. So if you want, you can, you should, I mean, should or you could, I don't know. It really depends on you. Normally I do this, I draw the curve so things would be clearer. Uh, so this, okay, so first of all, I wanted to figure out what little z is positive or negative, because this probability is really small, less than 0.5. So I know little z is actually on the positive side. It's kind of tail probability really small. So this area is 0.0274. From the table gives us accumulated probabilities. It's not the tail probability. I mean, the right tail probability. So left tail probability actually is also cumulative. But anyway, so I need to figure out this area, which is 1 minus 0.0274. That's 0.9726. 9726, which is here. So little z equals 1.92. Okay, that's the answer. What if this number is, say, uh, greater than 0.5, for example? If I have this number 0.9292, okay? So now this time I would really recommend you draw a graph, okay? So we have this is our 0. Uh, Greater than little z is bigger than 0.5. So this little z has to be somewhere here, okay? Because greater than, so this area is bigger than 0.5. If your z is here, then bigger than z would be here, and the area is less than 0.5, so that's not good. Okay, so you sort of need to figure out where the z is. All right, now using the symmetry, that is the same as the probability of capital Z less than negative z. Negative z is a positive number here, which is kind of, let me use a different color. So this is negative z, okay? And less than negative z, the areas to the left of this bar under the curve gets under the curve, but they are the same. So now you look at 0.9292. Well, I just look at this one. So it's less than, so it's cumulative. You have a 1.47, so it's 1.47. Sorry. And this is the probability. So negative z is 1.47. So z equals negative 1.47. All right. Okay, there another type of problem which involves an real interval which has two endpoints. For a general interval, the solutions may not be easy to find. Actually, there are possibly many solutions. So if I tell you this equals 0.5, then obviously uh, there are many solutions for A and B. So normally we have a symmetric type of interval. Then we are actually able to do that. For example, if we want to find, sorry, little z, okay, positive z, we're looking for z, then we're able to solve. Probably needs a little bit more work. So I have a negative z, positive z here. This is 0.5. So so I guess, so how can I do that? Okay, so the simpler way is probably to come up with 0.25 here, 0.25 here, and then everything to the left of positive z, that's a 0.75. And then you look at 0.75 in the table, 0.75. Well, it's kind of an average of these two numbers. So z would be 0.675 around. Okay. All right. So this is a type of problem you need to be able to figure out. So find z if probability of z less than some a is known. Z is known. Or greater than z, or in a symmetric interval, or outside a symmetric interval. That's not difficult. You may have heard of the 1.96 and so forth. So let's do that. Let's find the two very important, actually three important critical value. It's called critical value. Capital Z, X value greater than little z equals 0.9, 0.10 actually. Inside would be 0.9, outside 0.10. So z should be positive. So these two parts add to be 0.1. So each tail is 0.05, 0.05. And then to the left of this bar, the area is 0.95. So you look at the 0.95 on the table, it's probability. So you need to look at the main part of the table, 0.95. Where is that? 0.95, so something like that. So 1.645. So Z is about 1.645. Many people just use 1.65. Okay. This number is widely used in statistics. Another one is when you have the tail probabilities to be 0.05. Okay, and then so this is 0.025, 0.025. So to the left of this bar, which we are looking for actually, is 0.975. So you look at 0.975. Here, so it's 1.96. So Z equals 1.96. This is probably even more widely used as a critical value for statistics. And the last one, they're just commonly used, okay, is 0.01. So I have a probability of capital Z less than little z equals 0.995. Okay, the tail probabilities for both sides 0.01. So one tail would be 0.005. So one minus that is 0.995. Okay, the idea is very similar to these two graphs, so please check. What do I have for little z? 995. Let's look at 995. Okay, something like this. 2.58. I think normally people use 2.58. Okay, Z equals 2.58. All right. All right. So these are the critical values we use a lot in statistics. And then there's another rule called 90%. What is that called? 68, 95. No, 97.5 or something like that. I don't remember the rule. Basically, it's the probability between uh, within one standard deviation away from the mean. So let's calculate that, okay? Let me get rid of everything. So we're looking for the probability that Z is greater than -1, less than 1. It's a standard deviation of Z is 1, so it's one standard deviation away. So it's probability, let's use phi. I'm kind of introducing all these notations. Phi of 1 minus phi of -1, phi of 1, that's pretty easy. 0.8413 minus -1 is the left tail, so it's 1 minus 0.8413. It's 1.6826 minus 1, so it's 0.6826, and normally people just approximate it by 0.68, so 68%. People would say, oh, 68% of the data would be within one standard deviation away from the mean. And then the second one, z greater than -2, less than 2. Okay, it's a phi of 2 minus phi of a -2. Phi of 2, which is 0.9772 minus 1 minus 0.9772. That's 1.9. Minus 445 minus 1. So it's about 95%. Okay. And finally, 3 standard deviations away. I think it's 99.7. So let's see. Z less than 3 standard deviations within, okay, 3 standard deviations away from the mean. That is 3. So let's look at this. 0.9987 minus 1 minus 0.9987. This 0.0013, 0.9974. Okay, so it's about 9.7%. Okay, so all these numbers are actually coming from come from the standard normal distribution or general normal distribution. Um, if data shows some normality, then you can use these rules. But if the data doesn't show nicely about this pill-shaped curve, then it's not always good to use these numbers. Okay, so we have three types of problem. Find the and let's look at the next one. This is one type. We did that, and then another type, knowing. Oh, this is actually not good. This is actually Z. That's what I meant. And then repeat one with general normal distribution, which is kind of probability of Z greater than A, less probability of X, sorry. And then here you are looking for the critical values when for the general normal distribution. So let's look at an example for that one, and we're done with these four types of problems. Okay. So for example, I know the probability of x, say greater than little x equals 0. I just do some random number. Let's do 90. Okay. And x, I know it's normally distributed with mean 2, that's mean 3, and standard deviation 2. So it's 2 squared as the variance. So the idea is this: we're going to standardize x and little x, capital X, little x. So the probability of capital X minus 3 over 2 greater than little x minus 3 over 2. That equals 0.90. And then that's the same as capital Z greater than x minus 3 over 2 equals 0.9. So it's Z now. We can use the table. Okay. It's greater than some number is 0.90, 0.90. So that number is actually negative. So x minus 3 over 2, which this number is negative. It's on the right side. So you use symmetry. That means this is a negative x minus 3 over 2, and to the left side is also 0.90. So I look at 0.90 as as a probability. So where is that? I think this is pretty close. 1.28. So this number is 1.28. So this number is negative 1.28. So then I solve for x. So x minus 3 over 2 equals negative 1.28. X equals 3 minus 2.56 That is 0.44. Okay, that's our little x. That's how you get it. Uh, this is normally what I do. People just some formula like x minus mu over sigma equals z. So x equals z times sigma times z plus mu, and we find z from the table. Sure, that's fine. But eh, the explanation or illustration, they are here. Okay. All right. These are the four types of problems you need to know. Next, there's another fact. Uh, if X is normally distributed with mean mu1, standard deviation sigma 1, and Y has a normal distribution with mean mu2 and sigma 2 squared, and assume that they're independent. I didn't say it here, but let's say they're independent. X and Y are independent. Uh, Two random variables to be independent, we need to use different language to language which is not covered now to explain it. But for the moment, you just use the ad hoc method to just use the common sense to understand. It's basically x a random variable and y is another random variable. They are independent in the sense that what the value x takes has nothing doesn't contribute anything to do with the probability of any y in some interval. Okay, so uh, yeah, okay, that it's not very exact, but it's let me use this x plus I, an interval given y some interval that is the same as here ij are intervals. Okay, for any ij it holds. All right. This fact can be used to solve problems like, oh, so suppose Jack plays some uh, some game. What kind of game has the scores normally distributed? Yeah, okay. Let's just talk about SAT. Jack has a say the scores of Jack follows a normal distribution with mean Jack's score follows a normal distribution with mean say 200 and standard deviation. So it's probably not the SAT score, but I'm just doing it randomly. And the Jill's score is also normally distributed with mean 190 and the standard deviation probably 50 squared. And then you're looking for the probability that the sum of Jack's score and the Jill's score together is in some interval. So let's call this x, call this y. So we're looking for the probability of x plus y is greater than, I don't know, 390. So let's say 290 less than 500. Those are random numbers. So if we want to do that, so we need to use this fact, this another fact. So suppose we have two random variables which they are independent, both follow normal distributions, but with different parameters. Then x plus y also follows a normal distribution, with mean just mu1 plus mu2. And the variances, the variance of the sum is the sum of the variances. Okay. It's not true that the standard deviation of this equals the sum of the standard deviations. That's not true. They have the standard deviations have a sort of a Pythagorean type of a relation. which is that the sum of the squares equals the sum of the squares equals the square of the other one. Okay, so then you can use this fact to solve this probability. Basically, you just standardize it. Okay, so this, I'm just rewrite a little bit and then we're done. X plus y minus mu1, mu2, so that's 390. And divided by, it has to be the square root because the standard deviation is the square root of the variance. So you have 100 squared plus 50 squared. You do the same thing for 290. So 290 minus 390, and then divided by this number. And you do this the same for 500. Okay. And then this is actually our z because you standardize it, becomes a standard normal random variable, and you will get the number here. You get simplify it here, and you can use the standard normal table to find this probability. Now for x minus y, it's very similar. It's still normally distributed. So it's still normally distributed. Again, assuming these two, okay, they are independent as well. So it was normally distributed with the mean mu1 minus mu2. That's no problem. It is the variance that you need to be careful. Even though you have a minus sign, the variance would be still positive. So it's still adding, okay? Because the variance of a negative y is still the same as the variance of y. Okay, so you don't put minus here because what if the variance of x is smaller than the variance of y, then it would get a negative number, which is not good. Okay, I think it's probably too long. I'm going to stop here. There's another type of problem which is called normal approximation to binomial. I'll probably use a different video for this topic. Okay, that's for today. I'll see you later. Bye bye.